implicitly defined function and what an explicitly defined function is. So most everything that you have seen so far in your math career has been explicitly defined. So that would be, like in Math 1, it would be something like y equals 2x plus 3. Right? Later on, it might be something like f of x equals x squared minus 3x plus 2. Right? It could be something like we just looked at, where we've got like y equals, what do we just have? 3x minus 4 over the square root of x minus 2. Right? It could be very simple. It could be very complicated. What makes these all explicitly defined is that it is either given as like a y equals or f of x equals. It is solved for y, or sometimes they use an f of x notation instead of y. Those are all explicitly defined. You do look at a little bit of implicitly defined functions. The one that you have probably seen before, this would be Math 3. You should have seen something like x squared plus y squared equals 9. Okay, this would be an implicitly defined function because it is not like solved for a single variable. Does anybody know what that is the graph of? It is a circle with a radius of, not 9, 3. Right? So that would be the graph of a circle. We also could have a lot of other things. It could be something crazy like 3x squared minus 7xy plus 5y to the 5th equals x minus y, or something like that. That would be definitely implicitly defined. It is not solved for a single variable. And a lot of times, these problems can't be solved for a single variable very well. Now, you can see some different things there. Now, we have a little teensy-weensy tiny bit already been doing some implicit differentiation, but so little that you did not even notice that you were doing it. So, whenever we were taking the derivative of y equals 3x squared, and so if it didn't have f of x notation, there were a couple ways I told you you could write that answer. I told you you could either write y prime equals 6x or dy dx equals 6x. So, technically, y prime can be implicit differentiation as well. I don't like to use that notation, especially when we get to related rates. It becomes more difficult to deal with. So, I prefer this right here. You technically did implicit differentiation whenever you did that, because you took the derivative of y with respect to x. So, but you didn't know. You were just like taking a derivative, right? So, let's talk about what this right here means, the d over dx, that notation, okay? This means the derivative of whatever's in your brackets, in this case 3y squared, and then the bottom part tells you with respect to whatever variable you have here. In this case, it's x. Now, everything we've done so far, we've been taking the derivative with respect to x, and we are going to continue to only take the derivative with respect to x here for everything we're doing in this unit. When we get to Unit 4, we will do related rates, and we'll take derivatives with respect to something besides x, but we'll save that for when we get there. We are taking the derivative with respect to x. Now, whenever you do this, it is almost like a chain rule. So what you're doing up here, you're taking the derivative of y. So you have to write down that you took the derivative of like 1y, the derivative of like 1 and a variable is just 1, right? So like technically there could be like a 1 right there. But then you must take the derivative of the y with respect to x. And to show that you did that, you write dy dx. That's the derivative of y with respect to x. Okay. Over here, you're taking the derivative of this stuff. 3 times 2 gives you 6. Decrease your exponent by 1, you get x. And then you just took the derivative of x with respect to x. But it's unnecessary because dx over dx is 1 and not needed, right? So we don't ever write that, right? It would just like go away. So if you're taking the derivative of a variable with respect to that variable, you don't have to put anything special next to it. But if you're taking the derivative of a variable with respect to a different variable, you're going to have to include that piece. So here's what it will look like on this question. I am taking the derivative of the stuff with respect to x, but what variable do I have on the inside here? I have a y. So I take the derivative of that expression like I normally would. So in this case, 3 times 2 is 6, y squared. I just decreased my exponent by 1. I got 6y to the first power right there. But I took the derivative of this with respect to x. So I have to multiply this by a dy over dx. So basically, you're just going, anytime you take a derivative of something that has a y, you're going to have to put a dy dx with it. You don't have to do it with an x because it's a dx over dx, which is 1, and it just goes away. Okay? So, let's look at taking a couple derivatives here. So if I'm taking the derivative of example 1 with respect to x, I'm going to take the derivative of 3x. I'm going to do that just by saying 3. Do I need to put anything special with that? I do not, because I was taking the derivative of an x with respect to an x. So I don't have to put anything special with that. But on the second part, I've got 2y squared. What do I get when I take the derivative of 2y squared? 4y. So I get 4y. But I took the derivative of something that involved a y with respect to x. So out next to it, I've got to put dy dx. Okay, and when we start getting to full equations, we'll see like what this means a little bit more. But right now, we just leave it like that.
Why do you need to put it if it's like right there with d over dx? Like, what does it matter that you
Your variables have to match. So if they do not, it's almost like a chain rule, like you're taking the derivative, like your inside part is your y.
Oh.
So you're taking the derivative of the stuff, 4 times y to the first power. And then the derivative of the inside stuff here, which is the y, is dy dx. So it's required. Over here, it's not really required because if I take the derivative of 3 times stuff, it's just 3. But then if I multiply by the derivative of the x with respect to x, it's dx over dx, which is 1, and it's unnecessary to write that. So if you're taking the derivative, it's like a chain rule there. But if you're taking a derivative of a variable with respect to that same variable, it's unnecessary to write anything extra with it. But if you take the derivative of a y with respect to a different variable, which is what we'll be doing here, y's will be with respect to dx, then you'll need that. Okay. So if I look at the second one here, I'm still taking the derivative with respect to x. I've got x squared times y to the third. What do I need to take the derivative of that expression? Which rule would I need? It's going to be product. Does it need a chain? Not really, unless you're considering that dy dx to be a chain. It's just two things multiplied together. So x squared is your first, y to the third is your second. So when you take this derivative, you will have x squared times the derivative of y to the third. So the derivative of y to the third is 3y squared, but I just took a derivative of y with respect to x, so what do I have to put with it? dy dx. And then we'll have plus sign. Then we got our y to the third. You do not need a dy dx here because you're not taking the derivative of it, right? You're just restating the y to the third. And then I'm taking the derivative of x squared, which is 2x. And so there's not much you can do with this. They probably would clean it up and write it like 3x squared, y squared, dy dx plus 2xy cubed. They might factor out a GCF or something there. Probably not. It's not going to be helpful on what like our next step with this is, so I'm going to just stop there. Now, you will not really be asked to do what we've just done in example 1 and example 2 very much. What you're going to see these in are in implicitly defined functions, because this is not really a function, it's just an expression. There's no equal sign there. So what we're going to see is going to be more like number 3. Now, let's graph this. Like, these are not going to be calculator active, but I just like to see what some of these look like because they are cool. So, let's see what we got here for this. This is so great. Before Desmos, we couldn't graph these. So it makes that graph right there. I liked it better whenever it was just a 2. That's cool. You can make like crazy graphs by doing things like this. Like if I just do a random one, like if I do y to the third minus the square root of x plus 2xy equals 55. Oh, that's not very pretty. 5x minus y squared. Sometimes they look really cool. That one doesn't look cool. That one's really not impressive. But anyway, sometimes they look really cool. So this is not a function. It wouldn't pass the vertical line test. Like if you look right here, see how you got like these points right here that are over top of each other? It's not a function. So it has to be this implicitly defined equation here. So we have to, but we can still find the derivative that will give us the slope of the graph at any point, right? And that is our dy dx. So to do this, we will take our derivative with respect to x. So on both sides, we are taking the derivative with respect to x. And so when you do that, anything that has a y has to have a dy dx with it, right? So y to the third is just 3y squared dy dx. 4y is what we'll get for our next term, but it was a y, so we got to put a dy dx. What's the derivative of negative y? Negative 1 dy dx. Even if the y is gone, if you took the derivative of something that had a y with it, you must put dy dx, even if the y is gone now. Now, on this last term, I've got 5x squared, that's going to be 10x. Do I need anything special with that? No. Leave it alone. All right. What is the derivative of 20? 0. Okay. So what we want to do is we want to get an answer that's like dy dx, right? Equals. So here is how we are going to do that. We are going to move everything that has a dy dx over to the left-hand side. It's already there in this particular case. It's not always. And then we're going to move anything that does not have a dy dx to the right-hand side. So in this case, we just need to take that 10x and move it over here. Make sure you change signs of that 10x whenever you move it to the other side. So I'm just copying this stuff down. Like that. So, now, I have dy dx with every term on the left-hand side. That means I can factor out, step 3 here, my dy dx. And so over here, I'll just have 3y squared plus 4y minus 1. And over here equals negative 10x. And so if I want to get that dy dx by itself, it is multiplied by the stuff inside of the parentheses. I would need to divide both sides by 3y squared plus 4y minus 1. Like that. And I will get dy dx equals negative 10x over 3y squared plus 4y minus 1. Now, just like any other derivative, this gives you the slope of the tangent line at any point, right? The difference is you're going to need to know x and y coordinate for this, right? So, like, if we flip back over to Desmos just so we can understand kind of what's going on here, like, let's just pick a point on this graph. It would be great if we could have whole numbers, but let me do, I mean, I don't want to do that. It's going to have vertical tangent right there, I think. I think we're just going to have to pick some wild numbers right here. Let's do this. No, let me do that. Let's do x equals 3, and let's use that point right there. So let's do the point 3, what was that? Negative 3.0003. Okay, so, what was it? 900. Okay, so at that point right there, this point right there, if I want to know the slope of the graph, I would do negative 10 times 3, because that's my x-coordinate, over 3 times the y, let's copy that, squared, plus 4 times the y minus 1. So my slope of my graph there should be negative 1 point whatever here. If I want to write an equation of a tangent line, I could just do 1, or y equals this slope times x minus 3 minus 3.90003. And you can see that makes a beautiful, make a different color, a beautiful tangent line right there at that point. All right, so this equation still gives the slope of the tangent line. So if you had a point on the graph, you can plug that point into your derivative to get the slope of the tangent line at that point. Questions? right, let's do a few more. All right. What is this the graph of? Circle with a radius of 6. All right, so we're going to take the derivative of this one with respect to x. So when we do that, x squared, we just get 2x. Y squared, we get 2y, but what goes with it? dy dx. What's the derivative of 36? 0.
Is that most of the time going to be just equal 0?
A lot of times. Not always, but a lot of times.
So like they could throw in like...
They could make it like a 36x over there. They could. And then it'd be 36 there. All right, so we are going to now move anything that doesn't have a dy dx over to the other side. So 2y dy dx is going to equal negative 2x. And then what's the last thing I need to do? Divide by 2y. I would. In this case, those 2's are going to cancel out. So our dy dx is going to equal negative x over y. Does your radius of the circle matter here? If I did a circle with a different radius, would I get a different answer? No, I'd get the same answer here because that derivative of whatever the radius is becomes 0 here. Now, 5 is a little bit of a different question. 5 is still a circle. What's different about the circle? Shifted? Yep.
Yeah, to the right 5, to the left 2.
Right 5, not left 2. Down 2. Down 2. It's because that's on the inside of the parentheses. Normally, our ups and downs are not on the inside of the parentheses because we're looking at implicitly defined functions. But because that's on the inside of the parentheses, it's going to go opposite direction. So the center of this circle would be at 5, negative 2. What's its radius going to be? It'd be square root of 10, whatever number we would get for that. So it'd be square root of 10. So this is still a circle. Its derivative is going to be a little more difficult to deal with. Because what do we have to take the derivative of this? Chain rule. So here you thought it was gone, you thought we were done, but we are only just beginning. Chain rule. So on this, your chain rule, you're taking the derivative of the outside, and the inside is that x minus 5. So you got 2 stuff to the first power. The x minus 5 stays the same. What is the derivative of x minus 5? It is just 1. You technically don't have to write that 1, but I'm going to, just to be very clear about what's happening. And then we go to the next piece. And we need another chain rule, right? So I'm going to use some different colors. Here's our outside. Here's our inside part. So we would have 2 stuff to the first power. The stuff, the y plus 2, stays the same. What is the derivative of the inside of y plus 2? It's 1, but it has a dy dx with it because you're taking the derivative of something that has a y. And then on the right-hand side, what's the derivative of 10? 0. Not always equal to a number, but a lot of times it is. Make sure you make that a 0. A lot of people keep the 10 on accident there. Yeah, so right now, I could distribute this 2. So I've got 2x minus 10. Now, be careful right here. I'm going to write an extra step. That 2 and the dy dx have to get distributed. I'm going to combine them to dy dx. And then we've got y plus 2. So when you're distributing here, both of those terms have the dy dx. So it's going to be 2x minus 10 plus 2y dy dx plus 4 dy dx. What happens after this? What should I do next? Okay, anything without a dy dx gets moved over. Is it okay with you guys, since like I know this stuff is what's going to be left, can I go ahead and factor out my dy dx and then have 2y plus 4 right here? Just save a step right there, and then I'll have negative 2x plus 10. I'm going to move that over. Okay, what's my last step to get that dy dx by itself? Now, they probably will not leave the answer quite like this, because you could pull out 2 out of the top and the bottom. So that would be negative x plus 10 and y plus 2. 5, yes, thank you. There, and the 2's can cancel, so they'll probably leave the answer like this. They'll probably do 5 minus x over y plus 2. So, though this is quite a bit different. So, changing the radius of a circle is not going to change what the derivative looks like, because when you take that derivative on the first step, like even if we change the radius to 50 right here, it wouldn't change what the derivative looks like. But shifting the circle up, down, left, right, that's going to make a pretty big difference in your derivative there. Even though if you kind of look, this is kind of neat right here. Like, look at what, instead of having an x, we had an x minus 5. And instead of having a y, we had a y plus 2. If I take, this is just a side note. This might be dangerous to, I think it will work every time. I don't know, we'd have to write a proof to know for sure. My derivative was negative x over y. Well, if I took my x and changed it to an x minus 5, and my y and changed it to a y plus 2, I would get negative x plus 5 over y plus 2, which is what we got. So it's really like a shift of your derivative kind of there too, I guess. I think it'd work every time. I'd have to do a proof to know for sure, but we will not do that right now. I probably wouldn't, just in case. You're not going to run into like enough circles to know that as a hard, fast rule. So, because you'll see others that might look like this. This, it says, find the slope of the line tangent to x squared plus 3y squared equals 10 at x equals 1. So, we need to know the derivative, because slope of the line tangent, right, is the derivative. That is f prime, but we don't have f primes on this. That is our dy dx, and we want to know that at 1. But to be able to find that at 1, we're going to have to take the derivative. Okay, so x squared plus 3y squared equals 10. It's not very bad to take the derivative of this one. You're going to have 2x plus 6y dy dx equals derivative of 10 is 0. This is a relatively simple derivative, right? We're going to subtract that 2x, move it over to the other side, 6y dy dx equals negative 2x divided by 6y. They'll probably reduce it. Negative x over 3y. Okay? Now, that's our derivative. But what did they ask us for? That means slope. They did put an S here, making me think there's a possibility there's more than one point of the line tangent whenever x equals 1. So that means I need to plug in 1 to this, but what's the problem if I plug in 1? Am I going to get an answer? I have a y, right? So to be able to plug into this derivative, I need an x and a y coordinate. How could I find a y coordinate? 1 goes into the original, okay? So to find the y coordinate, 1 will go into the original. So I'll have to do 1 squared plus 3y squared equals 10. And so that is just 1 plus 3y squared equals 10. I would subtract that 1 from both sides. 3y squared equals 9. What do I do next? Divide the 3. So y squared is going to equal 3. And last step, square root. So y equals, I like what Connor's saying here, plus or minus the square root of 3. So the points that I'm using, I actually have 2 of them. I've got 1 square root of 3, and I've got 1 negative square root of 3. So you're going to have 2 answers to this question. So here's some important notation for you. If you want to find derivative at x equals 1 for, actually, let's do at x equals the point, let's not do x equals even. Let's do, if I want derivative at that first point, 1 square root of 3. Here's the notation that you're going to use. You're going to say dy dx, and you're going to use this line right here, and that line means such that. And then you need to do down here at the bottom of that line, you're going to do xy equals 1 square root of 3. So it's kind of weird notation. But this is what we do with dy dx notation, because it's not like function notation where we can do like f prime of x, where it's got that x and that y. This is how we're going to write it, and then we just plug in. So we would have negative square root of 3 over, I'm sorry, it's x. It's x on top. Let me start over. Negative 1 over 3 square root of 3. I would just leave it, definitely on FRQ, just leave it. You could rationalize the denominator. If you do, it'll be, if you do rationalize there, you would multiply by square root of 3 on top and bottom. So you'd have negative square root of 3 over 3 times 3, which will be 9. On a multiple choice question, they might do that. On a free response, definitely stop here. But that's only half of your answer, because you also need the derivative at 1 negative square root of 3. And so that we would, our notation will do dy dx such that xy equals 1 negative square root of 3. And we'll have negative 1 over negative, or what's that, 3 times negative square root of 3. And the negatives cancel out here, so it's going to be 1 over 3 root 3. Or they might do square root of 3 over 9 for that. But I would just, unless it's multiple choice and they've changed it, I would just leave it there. Okay, questions? All right, let's do this last one right here, because it's going to have, it's got it all right here. It's got almost all that could happen. It doesn't have a quotient rule, but it is going to have a chain rule on the left side. What's it going to have on the right side? Product right here. So our chain, like the outside of our chain, looks like this. There's our inside of our chain. So that will look like this. 3 times 2 will give us 6 times the stuff to the first power. That stuff stays the same, x squared plus y squared. But then we must multiply by the derivative of the stuff on the inside. So, yes. Yes, that is fine. Maybe one of those back desks back there would be good. Here we'll have 2x, and here we'll have 2y, but what does that y have to have with it? dy dx, because we're taking the derivative there. Okay, so that is my chain rule on the left side. On the right side, I'm going to have a product rule. I've got 100x, and I've got y. Or you can leave the 100 out and just do x times y, either one, but I'm going to put the 100 here. So I'll have 100x times the derivative of y. What is the derivative of y? dy dx. Plus the y times the derivative of 100x. What is that? 100. Okay, so now a lot is really going on here. To multiply these two things right here together, I've got to distribute. So that is going to look like this. For right now, I'm going to leave my 6 out front. So I've got to distribute. I'm going to have 2x to the third. Then I'm going to have plus 2x squared y dy dx. Then I got plus 2xy squared. And then over here, I've got plus 2y cubed dy dx. The right side, they'll just probably clean that up a little bit. 100x dy dx plus 100y. And so, if we distribute that 6, we'll get 12s for all those 2's, right? So, now we got 12x to the third plus 2x squared y dy dx plus 12xy squared plus 12y cubed dy dx equals 100x dy dx plus 100y. Do we have any like terms that can combine? None. No, we do not. So this is like a big mess. But at this point, long as you're just very careful, it really is not terribly difficult. We just need all our dy dx's on the left, anything without a dy dx on the right. So, like, we got this one and this one, they stay. That needs to move to the left. Yes. Yep. If you want, you can do that, and I think I will because I'm going to run out of room. So dy dx, kind of factor that out. I will keep a positive 12x squared plus a 12y cubed, and then I'll have minus 100x because when I move that over to the other side, it becomes negative. I'm holding on to these because these two right here don't have dy dx's. I need them to go over here. Oh, I did lose a y. Thank you. Okay, so the 100y, it stays where it was at. And then I will have minus 12x cubed minus 12xy squared. And then I'll divide. So when I divide, I'll get dy dx equals 100y minus 12x cubed minus 12xy squared over 12x squared y plus 12y cubed minus 100x. Now, this will reduce because everything is divisible there by 2. I'm going to pretend this is a free response question, okay? So if it is a free response question, you could reduce, but do you need to reduce? No. And if it is a free response question, they did ask me to answer this at 3-1. So I will need to plug in 3-1, okay? But we're going to pretend this is a free response question because otherwise I need another 10 minutes to do this, especially if I'm not letting you use a calculator. So xy equals 3, 1. That's our notation here. And then I'm going to plug in 1 for all the y's, 3 for all the x's. So it's going to be 100 times 1 minus 12 times 3 to the third minus 12 times 3 times 1 squared over 12 times 3 squared times 1 plus 12 times 1 to the third minus 100 times 3. And if it is a free response question, are we going to reduce this? Are we even going to attempt it? No, we're just going to leave it as our answer. Because if you can get to the answer of that without making a mistake, then good for you. But I'm going to bet that at least a third of you are going to miss it if we try it. Maybe more, maybe half. And you guys are pretty good math students there. So our assignment for tonight is going to be basically just taking some implicit differentiation problems here. It's going to be on 179, so this is a new page. You probably don't have a picture for it. You've got 1 through 15 odd. There. It does throw a little trig in there at the end. But just, if you take the derivative of sine x or sine y, it is just cosine y dy dx, right? So it just, anytime it has a y, just slap a y dy dx on the end. They're actually maybe possibly even easier because they don't usually simplify as much. Yeah. Simple. Even though these don't simplify terrible. These are not, the simplifying on this is not as terrible. You just have to be careful.